Hey there, and welcome to this explainer. Look, if you're a first-year engineering student currently staring down a massive mountain of totally intimidating textbooks, I want you to take a deep breath. Consider this your insider's cheat code. Today, we're going to strip away all that dense, heavy jargon to really master the fundamental properties of engineering materials. And trust me, by the time we're done here, you're going to be looking at the physical world around you in a completely different way.
Here's a quick look at our syllabus for today. We'll start with the Freshman Survival Guide, move into stress, strain, and deformation, tackle the stress-strain curve, explore elasticity with our rubber band analogy, cross the point of no return, and finally, my favorite, breaking stuff in the lab.
Section 1. The Freshman Survival Guide. Section 2. Stress, strain, and deformation. Okay, let's dive right into this by looking at the absolute foundational forces that change how a material behaves. Basically, stress is the force acting per unit area, and strain is simply how much the material's dimensions actually change in response.
Instead of getting totally lost in the pure math right out of the gate, let's visualize this. There are three main types of static stresses, and honestly, they're basically just physical actions. Tensile stress is pulling. Think of it like stretching a bungee cord as hard as you can. Compressive stress is squishing, like standing on an empty soda can. And shear stress, well, that causes adjacent parts of a material to slide against each other. Imagine holding the bottom of a deck of cards and pushing the top sideways. That's sliding action, that's shear stress.
Now pay attention here, because this right here is a classic freshman trap. In your classes, you are constantly going to hear about engineering stress versus true stress. Here is the difference. Engineering stress calculates force divided by the original cross-sectional area of the material. It's easy, it's a static number. But true stress, that calculates force divided by the instantaneous cross-sectional area. Why does that matter? Because if you stretch a piece of metal, it literally gets thinner in the metal. That changing, shrinking area means the true stress is actually higher than what the simple engineering math suggests.
Section 3. The stress-strain curve.
This brings us to, honestly, the most important tool in an engineer's toolkit. This curve is basically the ultimate treasure map for any material. As you move up the vertical axis, you're applying more stress, or force. As you move across the horizontal axis, you're seeing the strain, which is how much the material is stretching. This graph maps out the entire lifespan of a material under pressure, from a simple, bouncy elastic stretch all the way to absolute catastrophic failure. Right smack in the middle of that map is a massive landmark called the yield point. This is the exact moment a material crosses over from stretching elastically to deforming plastically. To picture this, just grab a metal paperclip. You bend it a tiny bit and it snaps right back. But if you push it just far enough past its limit, past its yield point, it stays bent forever. That permanent deformation is exactly what the yield point tells us.
Section 4. Elasticity. The rubber band. So, before we hit that yield point, materials act exactly like a rubber band. They just bounce perfectly back to their original shape. This perfectly reversible bounce back is governed by Hooke's law, which just means the strain is directly proportional to the applied stress. Visually, it's that straight, steep line right at the start of our graph. And the slope of that line, we call that Young's modulus, or simply E. Essentially, E measures exactly how stiff our metallic rubber band is. A super high E means it's rigid. A low E means it's incredibly stretchy.
Okay, let's put this into practice. Let's say we apply 276 megapascals of stress to a 305 millimeter piece of copper. How much does it actually stretch? Well, step 1, we look up Young's modulus for copper, which happens to be 130 gigapascals. Step 2, you simply divide your applied stress by that modulus, and that gives you your strain. Finally, step 3, just multiply that tiny strain fraction by your original 305 millimeter length, and boom, you have calculated the exact elastic stretch. See? It's literally just figuring out how far our copper rubber band stretches.
But wait, there is a physical side effect to all this stretching, and it's captured perfectly by Poisson's ratio. Think about our rubber band again. As you pull the ends to make it longitudinally longer, what happens to the width? Right, the middle naturally squishes inward. Poisson's ratio is simply the math behind that lateral squishing versus the longitudinal stretching. You pull it longer, it gets thinner, simple as that.
Section 5. Point of no return.
Let's see how this actually builds in physical reality once we pass that yield point. On the graph, you hit the ultimate tensile strength, which is the absolute peak stress a material can handle, and then the line literally starts curving downward before breaking. Look at what happens physically.
That downward curve corresponds to a phenomenon called necking. The metal literally forms this localized, thinned-out neck as it aggressively stretches right before it snaps completely in half.
You know, how a material snaps is honestly just as important as when. This beautifully contrasts brittle versus ductile materials. A brittle material like that steep red line snaps instantly with almost zero plastic deformation. But a ductile material, the long blue line, it stretches and stretches. That massive area under the ductile curve represents a ton of absorbed energy. We call that energy absorption tensile toughness. Ductile materials absorb the hit, brittle ones just shatter.
And this brings us to a really closely related property, hardness. Hardness is just a material's resistance to permanent indentation, scratching, and general wear. Now, having high hardness is absolutely fantastic for making tools that need to take a beating, but here is the ultimate engineering trade-off. Many materials that are incredibly hard are also extremely brittle, which means they cannot absorb much impact energy before just completely shattering.
Section 6. Breaking stuff in the lab.
So how do we take all this theory off the whiteboard? We get into the lab and we break stuff. We use universal testing machines to systematically apply forces. A tensile test slowly pulls the material apart. A compression test literally squeezes it. To measure that toughness we talked about, we do an impact test, which involves swinging a heavy pendulum hammer right into the side of a specimen to see how much sudden energy it absorbs. And for hardness, tests like the Rockwell test push a tiny point into the surface to measure exactly how deep the indentation goes. It is systematic destruction, all for the sake of science.
So, as we wrap up this explainer, I have a challenge for you. Take a second to just look at the objects around you right now. The legs of your desk, the screen of the device you're watching this on, the frame of your window. Can you guess which ones are brittle and which ones are ductile? Can you imagine the exact amount of force it would take to make them permanently yield? You now have the foundational cheat codes to see the hidden forces shaping the physical world. So keep questioning, keep analyzing, and keep exploring. Thanks for hanging out and learning with me today.